Hi everyone, and welcome to another video of this channel. So today we are going to investigate the integral of the arctangent of x dx. And we are going to do this with two methods. One will be integration by parts, and the other will be a more creative methods with derivatives. So let's get started with the integration by parts method. So I will first explain the method we will use here on a general case for any function f of x. Then I will demonstrate this method used on the integral of the natural log of x, and then I will finally solve our goal integral. So let's first look at the integration by parts formula. So it basically says that the integral of a function u of x times d v of x is equal to u times v minus the integral of v times du. So right now, let's just investigate the integral of any function f of x. Now our u would be the f of x, and then our v would be the x right here. So our v, dv, and then dx. So this is equal to u times v, which is f of x times x, minus the integral of v is x, d f of x, du, the other function. But the f of x is equal to f prime of x dx. And so basically we have that the integral of any function f of x dx is equal to f of x times x minus the integral of x f prime of x dx. Now, this there may not always be a closed form for this, right? I mean, there are a lot of functions that don't just have a closed form integral and may correspondingly not have a closed form of this integral. So this integral is not always evaluatable, but it is often much easier than this integral. So let's suppose, as an example, that f of x is equal to the natural log of x. Then the integral of the natural log of x dx is equal to, so the natural log of x, once again, is our u. Our x is our v. So we have natural log of x times x minus the integral of x, right, our v, the natural log of x. And the natural log of x is the derivative of the natural log of x dx. And the derivative of the natural log of x is 1 over x. But now the integral of x times 1 over x, well, that's just the integral of 1, which is x. So just like that, we have that the integral of the natural log of x dx is x times the natural log of x minus x plus c. So now, using this as inspiration, we will look at the case where f of x equals arctangent of x. That's our goal integral. So the integral of the arctangent of x dx, once again, this is arctangent of x times x, right? This is our u, this x is our v. And then we subtract from this the integral of x d arctangent of x. Now, d arctangent of x, that is the derivative of arctangent of x dx. So let's find the derivative of the arctangent of x, and in fact we will prove what the derivative of the arctangent of x is equal to. So the arctangent of x, right, that's the inverse function of the tangent of x. So let's just look at the derivative of just any inverse. And that, by the inverse of the derivative formula, by the derivative of the inverse function formula, is 1 over f prime of the inverse. Now, if f of x equals tangent of x, right, we know that the inverse of f of x is the arctangent. So the derivative of the arctangent, that's what we want here. So then f prime of x is 1 over cos squared x by the quotient rule. And then the inverse of f is the arctangent here. So now the derivative of the arctangent of x, well, that's equal to this right here. write 1 over cosine squared of arctangent of x, which is just cosine squared of arctangent of x. So now, if we just have any arbitrary right triangle, and this angle right here is the arctangent of x, then this opposite side right here is x, and this adjacent side is 1. So then the hypotenuse is the square root of 1 plus x squared. So then the cosine of this arctangent angle is adjacent over hypotenuse, which is 1 over the square root of 1 plus x squared. But because that is squared, we have that the derivative of the arctangent of x is 1 over 1 plus x squared. So now we can just plug this right here into this. So this is equal to arctangent of x times x minus the integral of x over 1 plus x squared dx. And now we can just use a u substitution. So if u is equal to the denominator right here, we have that du is equal to 2x dx. So then x dx is 1/2 du. And notice that x dx is this thing right here. And so we get that this is equal to x times the arctangent of x minus the integral of 1 over 2u, which in turn is equal to this right here, which is equal to this right here. And I dropped the absolute value bars because 1 plus x squared is always positive anyway, so we don't need them. And so we add the plus c, and this is the answer. Pretty cool, huh? But there is a more creative approach to this. I mean, this is absolutely a wonderful method that you should definitely use, but I'm going to show you a much more creative method. So this method will be using derivatives. So let's just once again investigate the integral of any arbitrary function f of x. And as in this approach right here, I am going to first demonstrate this method on an arbitrary function f of x. Then I'm going to use it as an example on f of x equals natural log of x. And then I'm going to do our goal integral. So for this derivatives method, basically the first thing we do is we hope there is a function g of x such that its derivative is equal to a constant a times x times the derivative of f prime of x, where once again f of x is the function whose integral we are trying to evaluate in the arbitrary case for this method. So now, once again, there is not always such a function g of x, but in the spirit of discovery, and maybe because sometimes this integral isn't always evaluatable. So in the spirit of discovery, we want to maybe experiment a bit and find out whether there is a function. So now what we do is we calculate the derivative of the product of x and f of x, which by the derivative product rule is equal to x times f prime of x plus f of x. So now we recognize x f prime of x as g prime of x over a. And now we subtract the g prime of x over a to the left-hand side of the equation, and the new equation is this is equal to this. So then if we subtract this onto this side and take the integral of both sides of the resulting equation by the fundamental theorem of calculus, we get that the integral of f of x dx is equal to x f of x minus g of x over a. And again, there may not always be such a function g of x, but we hope there is. So now I'm going to demonstrate this example on f of x equals natural log of x. So in this case, g prime of x is, we hope that there is a function g prime of x such that g prime of x is equal to ax times the derivative of the natural log of x. But then the derivative of the natural log of x is just equal to 1 over x. This x and 1 over x cancel, and we get a. And so g of x is ax plus c, right? Because if we take the integral of both sides, dx, we get that the integral of a dx is ax, and then we add the plus c. So now, by this formula right here, we have that the integral of the natural log of x dx is equal to x times the natural log of x. And then if we plug this thing right here into this, we have minus ax plus c all over a. And then this is equal to x natural log of x minus x plus c. And so that is, in fact, the same exact answer as we got in the previous integration by parts chunk of this video. So now, with this as an example, I am going to demonstrate our new method on f of x equals arctangent of x. So in this case, g prime of x would be ax times the derivative of the arctangent of x, and the derivative of the arctangent of x is, by our previous calculation, 1 over 1 plus x squared. So now, g of x, also by a previous calculation we did in the integration by parts part of this video, is a over 2 times the natural log of 1 plus x squared. Again, the absolute value bars are omitted because 1 plus x squared is always positive. And we add the plus c. Now, just to make one other point, this part right here is where the plus c comes from in the final integral. So now, we can once again use this formula right here. And we have that the integral of the arctangent of x dx is equal to x times the arctangent of x minus 1/2 times the natural log of 1 plus x squared. All of this plus c. And we are done, right? I personally thought that was pretty cool. So these are just two really great methods to find the integral of a function for which we may not have standard integration rules. And I think a very important lesson in both of these is, of course, in both of these methods, we don't know if there will be this integral, if the integral of x f prime of x dx will be defined. We don't know if there will be a function g of x such as its derivative is equal to ax f prime of x, but we try to, in the spirit of discovery, find these things because we refuse to be stuck on this one integral. So these two methods are, let's just explore methods if you are really stuck. So that's it for this video. I hope you like it. Thanks for watching, and I'll see you next time.